Welcome back. We have been discussing equilibrium constant. Equilibrium constant, which is a very important thermodynamic quantity, because not only from academic point of view, but from industrial point of view, this thermodynamic quantity derives a lot of meaning. As discussed in the previous lecture, in industry, it is important to have as much yield as possible, and equilibrium constant is nothing but the ratio of the activities of products divided by that of the reactants. And if activities are equal to concentrations, we generally write this as ratios of the concentrations weighted by their stoichiometric numbers. And then in industry, we are also interested in knowing how to optimize various parameters so that you can improve upon the value of equilibrium constant. In statistical thermodynamics, we are interested in connecting equilibrium constant with partition function, and that is what we have done in the previous lecture, where we connected equilibrium constant with molecular partition function by the expression which is given on this slide. Equilibrium constant is equal to product of Qjm naught by Na raised to the power stoichiometric number into exponential minus delta R E naught by RT. We also discussed that suppose if we apply this to this kind of reaction, A moles of A plus B moles of B in equilibrium with C moles of C, then how to write this K is the product J Q J M naught by Na raised to the power nu raised to the power g into exponential minus delta R E naught by RT, which is the same expression that is written above. But what I will do is, now I will put positive number for the products and negative stoichiometric number for the reactants. So, how we expand it? Positive for the products. Product is C, that means Q C M naught by Na. This will be raised to the power C into Q A M naught by Na raised to the power minus A. Pay attention to this. I am putting a negative sign because A is a reactant, into Q B M naught by Na raised to the power minus B, again because B is a reactant, then into exponential minus delta E naught by RT. This can further be written as K equal to, now I will write this as Qm by Na raised to the power C divided by Q A M naught by Na raised to the power A continuation into Q B M naught by Na raised to the power B into exponential minus delta E naught by RT. This is how we expand this product. That means it is a similar way of writing equilibrium constant as you have done in discussing chemical thermodynamics. That is, for the products you write in the numerator, and for the reactants you write in the denominator, and then there is an additional term which is an exponential term taking into account the difference in 0 point energy that has to come in this expression. Now, let us take an actual example. The question is, evaluate the equilibrium constant for the dissociation of Na2 going to 2Na. This is the reaction which is going on, which is given to us. This is dissociation of disodium at 1000 Kelvin from the following data. Rotational constant is given. Rotational constant means it is given for Na2 because Na cannot rotate. That is given as 0.1547 centimeter inverse. Vibrational wave number, that means this is also given for Na2, that is 159.2 centimeter inverse, and you have 0 point dissociation energy, that is also for Na2, that is 70.4 kilojoules per mole. Further, it is given to us that the sodium atoms have doublet ground terms. That means the degeneracy of electronic states for sodium atom is 2. This is the data given to us. We are supposed to find the equilibrium constant for the dissociation of disodium to sodium at 1000 Kelvin. How we will approach this problem is, first we will write an expression for K. As we just discussed, we will write K for Na square by Na square divided by Q Na2 divided by Na, right. This is for the numerator. I am already squaring it. This is for the denominator, and then I have exponential minus delta E0 by RT. This is now equal to Q square Na divided by Q Na2 into 1 over Na. This Na is Avogadro constant, not sodium, into exponential, instead of delta E0, let me write D0 by RT. What we have is the ratio of partition functions for sodium squared divided by partition function for disodium 1 by Na, which comes from this Na square and Na, and then exponential term is there. Now you remember that Na is an atom, sodium atom, and then you have QNA2. This is a disodium, that means it is a molecule. So therefore, we have to carefully decide what contributions come in. For atom, you have only translational contribution and you may have the electronic contribution. So therefore, what I will do is, I will write here that Q of sodium only, that means Q translational sodium square into, if there is degeneracy of sodium, divided by I have Q translational for disodium. Now remember that this is a molecule. So it will not only have translational degree of freedom, you will also have rotational disodium. You will also have vibrational disodium. Into 1 over Na is already there. Into there is 1 over G Na2 square into is exponential minus d0 by RT. So since we are talking about Na2 in equilibrium with 2Na, and we write the equilibrium constant is Q translational of Na square into degeneracy of the ground state for Na divided by Q translational for Na2 into Q rotational Na2 into Q vibrational Na2 into electronic contribution degeneracy of Na2, and there was 1 over Na term, and then there was exponential minus d0 by RT. So we have this expression. Now we very much know that Q translational is Vm naught by lambda Na cube, but this is squared. This is for the translational contribution. Then degeneracy of Na I will retain like this. In the denominator I will write Vm naught, because everything we are treating as ideal gas, divided by lambda cube of Na2. This is translational contribution. I will retain rotational, as such I will write Na2 into Q vibrational, I have Na2 into degeneracy of the ground state Na2 into 1 over Na into exponential minus d0 by RT. Please note that I am writing here standard state conditions, because although I am not writing not with all the Q's, it is understood that these are all the standard state quantities. Now let us try to further solve it. So now I have K is equal to Vm naught square by Vm naught. I will just write Vm naught, right? One is square, one is one term. And here only let me include Na. I will just bring Na along with this. Now what I have is lambda Na2 cube over lambda Na 6. This is the ratio of the thermal wavelengths into G of Na over G of Na2. This also let me combine into 1 over QR Na2 into QV Na2 into exponential minus d0 by RT. This is what I have. Now we can further work upon this and see what we get. P V m naught is equal to RT. I am consuming N because Vm, M means molar. So can I write this R is equal to K times Avogadro constant into T. R is K times Na. So therefore Vm naught by Na, this is what I want, is equal to Kt T by P naught, right. This is also not, because this standard state we are talking about. So Vm naught by Na, this Na is Avogadro constant, is Kt by P naught. So instead of this I can write Kt by P naught. If I write Kt by P naught, then I do not need the volume, because we are considering the standard state conditions and applying the ideal gas equation P naught V naught is equal to RT, I can get Vm naught by Na in terms of Kt by P naught. K is a constant, T is a given temperature, P naught is 1 bar. That means you need not be given the volume. Once I substitute this Kt by P naught over here, then I have this Kt by P naught into ratio of the thermal wavelengths, ratio of the degeneracies of the ground state, electronic ground state, and then I need the information about the rotational partition function, I need the information about vibrational partition function, and I also need the dissociation energy, 0 point dissociation energy, and that is what is written in this expression. Kt by P naught, you have this is Gx square, not Q, Gx square, lambda x2 cube, Gx2, Qrx2, Q vibrational x2, lambda x6 exponential minus d0 by RT. That means now the next problem is to evaluate the thermal wavelengths, rotational partition function, vibrational partition function, and then proceed for the calculation. The data given to us for lambda, lambda is equal to beta h square by 2 pi m square root, which is equal to h by 2 pi m k t square root. Beta is equal to 1 over kt. H is Planck's constant, we know 6.626 into 10 raised to the power minus 34 joule per second. K is Boltzmann constant, 1.381 into 10 raised to the power minus 23 joules per Kelvin. T, the temperature given to us, so we can calculate the thermal wavelength. From the knowledge of the masses of Na2 and Na, thermal wavelength can be calculated. By using this formula, the thermal wavelength of Na2 comes out to 8.14 picometer, whereas that for Na itself, the sodium atom, it comes out to 11.5 picometer. This can be obtained by appropriately substituting the numbers over here. All right. So we know how to deal with the thermal wavelength. Q rotational. Na2 is a linear diatomic molecule. So therefore the expression that you require for the molecular partition function is that for a linear rotor. And we know that QR for a linear rotor is 1 over sigma h c beta b. Remember that this equation is a high temperature result. That means your temperature, if it is much higher than the characteristic rotational temperature, then only you will use this equation. That means what you will do is you will use this equation K theta r is equal to HCB, calculate the value of theta r, because you are given Planck's constant you know, speed of light you know, and the rotational constant you know. The Boltzmann constant also you know. Substitute these numbers. and get the value of rotational temperature. You will see in this case where the temperature given is 1000 Kelvin is much higher than rotational temperature. You calculate and check yourself. Yes, it comes out to be the temperature, given temperature is much higher than the rotational temperature. So that means I am justified now to use this expression QR is equal to 1 over sigma Hc beta B. We are dealing with Na2, let us say. First we will talk about Na2. So if I put like this Na, a rotation by 180 degree leaves the molecule in an unidentifiable state. Therefore, in complete one rotation, the same state will appear twice. That means sigma in this case is equal to 2. You know the value of sigma now. You know the Planck's constant, speed of light, beta is 1 over kT and B is given to you. Once you substitute this, you will see that you get a QR value of 2246. Sodium atom is atom. You cannot have rotation in that. That means we don't need to worry about the rotational contribution to Na. Now comes vibrational contribution. Again, sodium atom cannot vibrate, but sodium molecule can vibrate. So when we discuss about vibrational contribution, disodium linear molecule. So normal number of modes of vibration is 3n minus 5 is equal to 6 minus 5 is only 1. One normal mode of vibration. One normal mode of vibration. And now if we look at the problem statement, rotational constant is given. We have already used that in calculating the rotational partition function. Vibrational wave number is the given, and we are also given that sodium atoms have doublet ground terms. So by using QV is equal to 1 over 1 minus exponential minus beta Hc nu bar. This is the expression to be used. Remember this expression which I have written over here, this can be used at any temperature. There is no high temperature approximation used over here. An alternate way of calculation can be just like you evaluated the value of rotational temperature. Similarly, you evaluate the value of vibrational temperature from K theta V is equal to Hc nu bar. Calculate theta V, compare with temperature, and then use the high temperature result. Not required, because this is a very simple expression. You know beta is 1 over kT, you know Planck's constant, you know speed of light, and we know the vibrational wave number. Once you substitute these numbers, what we have is 4.885. This is the number that we are going to get. Third one, the degeneracy of the electronic ground state for sodium atom is 2. The degeneracy for the ground state, electronic state for disodium molecule is 1. So by now we have everything. Qt can be calculated from V m naught by lambda cube, but in fact you don't need to calculate, because the expression that we are going to use, K is equal to K times T, this is G x square, ye lambda x cube 2 P naught Gx2, Qrx2, Qbx2, lambda 6. We know this, this, and dissociation energy is given to us. Let us look at whether it is given or not. The 0 point dissociation energy is 70.4 kilojoules per mole. Therefore, since we are given the value per mole, you will use d0 by RT. If it were given per molecule, then you would have used d0 by KT. The value of P naught is equal to 1 bar. This is because we are invoking standard states. Why standard state? Because in our all calculations which or the expressions are based upon delta G naught is minus RT log K, and we have connected everything with the standard state or change in Gibbs free energy under standard state condition. And when we say standard state, then we are saying it is 1 bar pressure. So now we have all the information. The given reaction was disodium going to 2Na, and from the knowledge of K is equal to pi j Qjm standard state by Na. Exponential minus delta R E naught by RT by, we used this expression, and then that expression was converted into this particular expression, and then by substituting the various numbers at 1000 Kelvin, P naught, you see here, when you solve the numerical problems, make sure that you are using the appropriate units. If you do not put the appropriate units, your final answer is going to be wrong. The given pressure P naught is equal to 1 bar, and then you have converted this bar, 1 bar, into pascals, 10 to the power 5 pascals. Why you introduce Pascal is because it will take care of the units. All right. So you have Boltzmann constant, you have temperature, you have this degeneracy factor, you have this ratio of the thermal wavelengths, and then you have this rotational, and then you have vibrational contribution. Everything put together, you see at 1000 Kelvin the value is 2.42. What we have done is that we have calculated the values of various molecular partition functions, substituted those values, we used the value of dissociation energy, and we can easily get the value of equilibrium constant. The value of equilibrium constant obtained here is not very high, only 2.42. That means this reaction does not have a high, very high yield. The delta G naught of this reaction is not very highly negative. Now it is a different matter how to improve this value. Improving the value of equilibrium constant depends upon various factors. For that you need Le-Chatelier principle. But in this case, what we have done is we have restricted our discussion only to equilibrium constant. So therefore, just to recap, what we have done is that by starting with this equation, we have identified that what different contributions go into the molecular partition function, and from those contributions what we have done is evaluated this equilibrium constant. The calculations may appear little lengthy, but the procedure is very simple. Only you need information on translational contribution, which depends upon the thermal wavelength, rotational contribution, vibrational contribution, electronic contribution, and the difference in 0 point energies. Once you have this information, the calculations of equilibrium constant is very easy. We will take some more examples to further clarify about what factors go into the evaluation of equilibrium constant. Remember that this equation is very simple, where you have only diatomic sodium and you have sodium atom. If you have a reaction in which there are triatomic molecules and multi-atomic polyatomic molecules, the situation can be complex. One such example we will take and further discuss, but that we will do in the next lecture. Thank you very much.